So for Chapter 7, we're going to be looking at Thermodynamics and Kinetics. Thermodynamics is the study of energy, work, and heat. There are three laws of thermodynamics. The first being that energy cannot be created or destroyed. It can only be converted from one form to another. The second one is the universe spontaneously tends towards increased disorder. So what that means is it's random, right? If I were to drop a bag of marbles, they would not fall and land in a perfect circle or even in a group. They would spontaneously go everywhere. So it's the measure of randomness, and this measure of randomness is called entropy. The last law of thermodynamics is that disorder of a pure crystal at 0 Kelvin is 0. So when we talked about Kelvin, way back I think in Chapter 1 when we did temperature conversions, 0 Kelvin was referred to as absolute zero. So this was the lowest achievable temperature. So that third law is just saying that if we reached 0 Kelvin, all disorder would be gone, basically because everything would be completely frozen in its place. So these laws of thermodynamics help us decide whether a chemical reaction is spontaneous or not. So let's look at a chemical reaction in energy. So we have a system, and when I'm talking about the system, it's the process under study. It's the reaction, whatever's in the test tube, or the instrument that we are using at the time. The surroundings then is the rest of the universe, so the air around the system. We have two types of reactions that we're going to look at, and one being exothermic and the other being endothermic. So when I say two types of reactions, I'm not talking about how in the previous chapters where we classified reactions as synthesis or decomposition, single and double displacement. No, these types are types of energies. Okay, so for an exothermic reaction, that is where heat is released to the surroundings. So how do you know if heat is released? Well, this would be, for instance, if you were holding the flask or the test tube that the reaction was occurring in, if that reaction flask heated up, like you felt it get warmer in your hand, that would be signs that it's an exothermic reaction because heat has been released, thus making your hand feel warmer. So how do we represent this in a chemical equation? So an example of an exothermic reaction is this combustion reaction. And I know it's combustion because I have a hydrocarbon reacting with oxygen to form carbon dioxide and water. So this is an exothermic reaction. Heat is released. So how we represent that is by putting here in yellow this 211 kilocalories. Okay, and what that is, that's heat. That's how much heat was actually released. We're going to look at some equations and actually be able to solve for heat so that we can know exactly what this amount should be depending upon the reaction. So if the heat is on the product side, such as in this case, it's an exothermic reaction. So now let's look at an endothermic reaction. So endothermic is when heat is absorbed from the surroundings. So let's go back to that idea of holding a test tube or a flask in your hand in which the reaction's happening. Now, if you were holding an endothermic reaction, you would feel the flask get colder. The reason for this is because that reaction is actually absorbing heat from the surroundings, and the surroundings is your hand. So by taking heat away from your hand, you feel your hand feels colder. So to represent heat being absorbed into the system, we place the heat in kilocalories here in yellow on the reactant side of the equation. So if you see this kilocalories or heat on the reaction side of the equation, it's an endothermic reaction. If you see the heat on the product side of the reaction, meaning heat is being released, it's an exothermic reaction. So this is just one way that we're going to be able to determine whether a reaction is exothermic and endothermic. We're going to look at a few other ways. So enthalpy. Enthalpy is another way which we can figure out if a reaction is endothermic or exothermic. So what is enthalpy? Well, first off, it's represented by the letter H. So that's the variable that we're going to look at representing enthalpy. So if you see H is equal to something, that H is enthalpy. Okay. Now, enthalpy, by definition, is the heat stored in chemical bonds. Okay, so in order to form chemical bonds, energy is needed. When chemical bonds are broken, energy is released. Okay, and it is released in the form of heat energy. So change in enthalpy is what's going to help us figure out if a reaction is endothermic or exothermic. So to get change in enthalpy, it's represented by this delta H. The symbol delta H means change in. So whenever you see a triangle in mathematic or chemical formulas, it means change. So change is always final minus initial. So to figure out delta H, we're going to take the enthalpy of the products, which is the final result of the reaction, and subtract it from the enthalpy of the reactants, which is the initial part of the reaction. So final minus initial, in this case, products being the final minus reactants being the initial. And most of the time, the enthalpy will just be given to you. It's not necessarily anything you need to calculate. The important part of this slide is to know that if that delta H that's given to you, that change in enthalpy, is positive, that indicates an endothermic reaction. If the delta H is negative, that means it's an exothermic. So we're going to learn how to calculate heat. So this heat that we've been talking about that's involved in chemical reactions that determines whether the reaction is endothermic or exothermic can actually be calculated using the following equations. And it's to calculate heat, we usually use what we call calorimetry. And what that is just a process that measures the heat transfer in a reaction. Okay, it's a closed system process where we try to stop heat from escaping the system, and we try to avoid heat from entering into the system to get an accurate heat value. So to do that, we're actually going to be taking this equation shown here, where we have Q is equal to mc delta T. Now Q, that is heat, so that's the variable for heat. So if you have to calculate Q, you are calculating the heat. As for the rest of it, mc delta T. So notice we're seeing that delta sign again, that triangle. So all that means is we need to know the change in temperature to calculate heat. So the equation right below just wrote that delta T out in a longer form. So delta T is change in temperature. Change in temperature is always going to be the final minus the initial. So it's our job to read the word problem and figure out of the two temperatures given, which one is the final and which one is the initial. When we are using temperature in these equations, notice below it is in degrees Celsius. Okay, so if it's not initially in degrees Celsius, we need to convert it to degrees Celsius. The m part of this equation is mass, and the mass needs to be measured in grams. If it is not in grams, then it needs to be converted into grams before it can be inserted into the equation. And last but not least, this variable represented by the letter C. And what that is the specific heat. These are values that you'll get from a table, or else they'll be just given to you in the word problem itself. And what specific heat is, it's the capacity of that system to absorb heat. So it's dependent upon what type of material we're talking about. Different materials have different specific heats. Water, for instance, has a specific heat of 1 calorie. So let's look at a table of specific heats just so we can understand where this value is coming from a little bit better. So remember when I said specific heat, that's the letter C in this equation in yellow here. So different substances have different abilities to absorb a given amount of heat. So the definition is how much heat energy is required to change the temperature of a substance by 1 degree Celsius. So first, I want you to look, let's notice the units on the specific heat. So looking at the table, looking at this calories per gram times degrees Celsius. So if nothing else, specific heat is really going to help you remember what all the units in the equation are. So the Q value, or the heat, is measured in calories. The mass is measured in grams. And then the temperature, degrees Celsius. So looking a little closer at these values here. So it's how much heat that material can absorb before the temperature of that material increases by 1 degree Celsius. So a good example would be if you are going to go outside on a hot day, would you rather step out onto a metal deck or onto a wood deck? Okay, I personally would prefer the wood because I would assume that the metal is going to be too hot for my feet to handle. All right, so why is this? Because it's the same sun hitting both objects made of two different types of material. The reason for this is the specific heat of that object. So how much heat can they absorb before that object will increase in temperature? So the metal deck, let's say it's made of aluminum. Well, looking at the specific heat of aluminum, it's 0.215. That means it can absorb 0.215 calories of heat before it increases by 1 degree Celsius. Okay, well let's look at the wood. Notice the wood has a higher specific heat, 0.4, almost twice as large. That means that wood can absorb twice the amount of heat before the temperature of it will increase by 1 degree. Water, once again, that I mentioned on the previous slide, has the highest specific heat on this table here. So water can absorb a lot of heat before its temperature raises. So in these practice problems, we're going to be calculating heat, that Q value, and we're also going to use that, take it a step further to figure out if a reaction is endothermic or exothermic. That's the big part of this chapter, is using different tools, either reaction diagrams, change in enthalpy amounts, or even the heat values to figure out if a reaction is endo or exothermic. So I have a video where I've worked through these problems, so you probably want to watch that after looking at these PowerPoints and work through them. Now let's look at kinetics. So we've done the thermodynamic portion of the chapter, so we're going to now apply it to kinetics. So the definition of kinetics is the study of the rate of chemical reactions. So how fast does this reaction happen? Is it quick? Is it slow? Does it take a while? So to figure this out, we're going to use the activation energy, or energy of activation. And that's represented by the symbol E sub A, for energy of activation. And what this is, it's a minimum amount of energy that is required to start a new reaction. So the higher the EA, the activation energy, the slower the reaction is going to go. So let's look at this with a diagram, because visual is going to help us solidify this term. So EA, the activation energy, is the energy required to get a reaction started. All right, so in this specific diagram here, we have the reactants on this side. Okay, so our reactants are the beginning. Then those reactants have to climb over this hill, which is the activation energy hill, before the reaction can start. So the smaller the hill, the faster the reaction, which makes sense because it's harder to climb a large hill than it is to climb a small hill. So those reactants have to climb this hill, this activation energy, to get the reaction started. Now the products in this specific reaction energy diagram are down here. So our EA is the amount from the reactants to the top of the hill. So reactants to the top of the hill is our activation energy. From these reaction energy diagrams, we can also figure out what the delta H is. So delta H, that change in enthalpy that we are going to use to help determine whether reactions are endothermic or exothermic, is represented on this diagram, and it is the distance from the products, so the products being here, if I could draw a straight line all the way over, you'd believe me, all the way up to the reactants. That's your delta H. You remember when we said delta H was change in enthalpy? Well, change is always final minus initial. And we said the final was the products and the initial was the reactants. So it makes sense that that would be the distance from where the products are up to where the reactants are. When we're given this change in enthalpy, just a reminder, if it's negative, it's going to be exothermic. If it's positive, it's going to be endothermic. So looking at this reaction, I can figure out a number of things, this diagram. First, I can look at the activation energy, the hill, from the reactants up to the top of the hill, and tell if this is going to be a slow reaction or a fast reaction. I can also tell, with that delta H, if it's going to be an endothermic or an exothermic reaction. So looking at it, the reaction is exothermic. How do I know that? Well, by looking at the diagram, I can figure out if the enthalpy is going to be negative or if it's going to be positive, because my reactants are higher in energy than my products. So if my products are lower in energy, say they have an energy of 5, well, my reactants are way higher, so let's say their energy is 15. Okay, well, if delta H is products minus reactants, I'm taking my 5, my low energy down here, and I'm subtracting the energy of the reactants, which I just said is 15, and I'm just making these numbers up. Okay, if I take 5 minus 15, am I going to get a negative or a positive number? I would get negative, right? 5 minus 15 gives me negative 10. So negative number, or negative delta H, is exothermic. So that's how I know just by looking at this diagram. So the rule is, if your products are lower in energy than your reactants, you have an exothermic reaction. Likewise, if we were to switch that and your reactants were lower in energy than your products, it would then be endothermic. Another piece of information on this diagram also tells me it's exothermic, and that's the chemical reaction. Notice I have the heat on the product side, and at the beginning of this chapter we said that if the heat's on the product side, then it's an exothermic reaction because that means heat's being released. So let's look at a few more reaction energy diagrams and kind of pick them apart so we can get used to what type of information we can glean from them. So in this first one here, remember the activation energy is the energy needed to get the reaction going. And that's always the distance from where the reactants are up to the top of the hill. So in diagram A here, my activation energy is pretty large compared to the last one. It's a fair distance. So I would assume that reaction A is going to happen slowly because it has a long way to get to the top of that hill. So the activation energy tells me the rate. It's going to be slow. Well, looking at A, the change in enthalpy will tell me if it is endothermic or exothermic. Okay, well in this case my products are higher in energy than my reactants. So if the products are higher in energy than the reactants, that means I'm going to have a positive delta H, and that tells me it is an endothermic reaction. So let's look at B, reaction B. So this reaction energy diagram, I have my activation energy from where my reactants are to the top of the hill. So this activation energy, this hill is smaller, less than A. So I would expect reaction B to happen faster than reaction A because the activation energy, this E sub A, is smaller. To figure out if it's endothermic or exothermic, I'm looking at the delta H. And in reaction B, the products this time are lower in energy than the reactants. If the products are lower in energy, I'm going to get a negative delta H. Negative delta H tells me that it is going to be an exothermic reaction. So the answers are written below. So now let's look at a problem that you might see on an exam regarding these activation energies, reaction coordinate diagrams. So the question here is asking you to circle the reaction that depicts a slow exothermic reaction. Well, slow, for that we're going to look at the activation energy, the E sub A. How big is the hill from the reactants to the top of the hill? For exothermic, we're going to look at that delta H, and we're going to figure out if it's positive or negative depending upon where the products and reactants are. So in this first one, let's look at A. So the reactants are always on the left-hand side, just like if we were writing a chemical reaction. And we have to go all the way up to the top of the hill. So that's a huge activation energy. Okay, well, that means if it's a huge activation energy that it's going to be very slow reaction. It's got a long way to get to the top of the hill. So A is a possible choice because it's slow. Well, now let's look and see if it's exothermic or endothermic. So in this case, we have our products higher in energy than our reactants. If our products are higher energy than our reactants, we're going to get a positive delta H. And positive delta H is endothermic. So I can safely say that A is not our answer because it is an endothermic reaction. Okay, let's look at B. So for B, my activation energy is from the reactants on the left-hand side to the top of the hill. Very short distance, right? So it's going to be fast. So I can X that one out right away just because it's a fast reaction. It has a low EA. Looking at C. Okay, well, from reactants to the top of the hill, fairly large distance, so it would be a slow reaction, so it's still in the running. Well, now let's look at the delta H, which is the distance from the reactants down to the products. So in this case, my products are lower in energy than my reactants, making my delta H negative. Negative delta H is an exothermic reaction, so I'm going to go ahead and say this is our choice. We're going to look at D anyway, just for fun. So in this one, from reactants up to the top of the hill, our activation energy, very large. So yes, it is slow. However, my products are higher in energy than my reactants, even if only a little bit. So this is going to have a positive delta H, and this is an endothermic reaction. So C is the correct answer. Now we're going to look at some factors that affect rate, so that affect how fast the reaction happens. So one of the factors being the structure of the reactants. If you have dissociated ions, they're going to react a lot faster than if you have two solids together. This was actually a question on one of our labs. It asked why did we not just combine copper sulfate and iron in their solid forms? Well, we could have, and the reaction would still have happened, but it would have just been really slow. So the reason we dissolved that copper sulfate in water was to dissociate those ions and get that reaction to happen faster. Another factor affecting rate is the molecular shape and orientation. What this means is if you have really bulky groups, it's hard to get the elements you want reacting close enough to each other to make that reaction happen. The third one, concentration. If you increase the concentration, the reaction is going to happen faster. Why? Increased concentration means you have more of those molecules around. The more molecules you have available for the reaction to happen, the faster that reaction is going to happen. Fourth one, temperature. For the most part, higher temperature will make the reaction happen faster. And this is similar to concentration because you just have more collisions between the molecules. If you have a higher temperature, what happens is those molecules start moving around more and moving around faster. If they're moving around faster, then they're going to run into each other more, and the probability of the reaction happening will be higher, increasing the rate. The physical state of the reactants, also a factor. Okay, this is similar to when we were looking at the aqueous for Rule 1. So if you have gases and liquids, those happen very fast. Solids, very slow. This is just because in the gas and liquid phase, your molecules are moving. If they're moving, they're going to come in contact more often, and the probability of the reaction is higher. If you have two solids, that's going to be a lot slower. You're going to have to sit there with a mortar and a pestle and grind away at them to get those solids moving and in more contact so that the reaction can happen. Now this last factor that we're going to talk about, we're going to expand upon, a catalyst. So this is something we haven't heard of before. What a catalyst is a substance that's going to increase the rate of the reaction. So it's going to make the reaction happen faster, and it does this by lowering the activation energy, that E sub A that we were looking at in all of those reaction coordinate diagrams. Now what's special about a catalyst is it's not consumed in the reaction, and it doesn't change the products. So whatever your catalyst is that you put into the flask, that same catalyst you can get out at the end. Nothing has changed it. It just helps the rate of the reaction. So here we have two examples that kind of show the path of the reaction and the effect that a catalyst has. So the catalyst increases the rate of the reaction, makes it go faster. We also said the catalyst is not consumed. So you can kind of envision this as the reactants are trying to go over a hill. Right? A tall hill is going to be harder to go over. It's going to take longer, making it slower. Well, what a catalyst does is it just gives those reactants a different route, a way around the hill, so a smaller hill, if you will, making that reaction happen faster. So this is just showing two other examples of how a catalyst works. So let's look at a reaction coordinate diagram and how a catalyst can change the appearance of a reaction coordinate diagram. So in red, we have the reactants going to products. The activation energy being the distance from reactants to the top of the hill. So in red is without a catalyst. If a catalyst is added, what happens is that activation energy is lowered, and we're looking at the green pathway. Now the distance from the reactants to the top of the hill is much smaller, allowing that reaction to go faster. Over in the second reaction coordinate diagram, this is just a different way that a catalyst can affect. So instead of decreasing the activation energy as a whole, it breaks it up into smaller, more manageable pathways. And the overall activation energy result is still smaller. So let's talk about reversible reactions and how equilibrium can be affected. So many reactions are reversible or do not go to completion. So far in this class, we have looked at reactants going straight to products, period, end of story. Well, that's not always the case. So there are reversible reactions, and all a reversible reaction means is that we don't always just go from reactants on the left-hand side of the equation to products, and then that's it. Sometimes those products revert back into their original form. So this is called an equilibrium, and it's represented by an arrow going in both directions. So there's an arrow going from reactants to products, but there's also an arrow going from products to reactants. So this example here is showing sugar. So you can take sugar, solid sugar, and dissolve it in water. When you do that, the sugar is now considered to be aqueous. So aqueous is just a solid dissolved in water. Okay, well, we talked about dynamic equilibrium, and we said, going back to the Kool-Aid, that that sugar that's dissolved actually comes out of solution to form a solid at the bottom. So it is going in the reverse direction. So equilibrium is a reversible process, and it occurs in dynamic equilibrium. So we have this definition again. We're going to see it several times in the next few chapters, so this is an important definition for you to know. And what dynamic equilibrium is an ongoing process of sugar molecules dissolving and precipitating out. And it's not just sugar molecules, it applies to several other examples. Okay, so the important part of dynamic equilibrium is that this ongoing process of the dissolving and the precipitating out is happening at the same rate. So the rate of the forward reaction is equal to the rate of the reverse reaction. Let's look at another example of a reaction at chemical equilibrium. So what we have here is nitrogen gas and hydrogen gas combining in a synthesis reaction to form ammonia. Well, this is an equilibrium reaction, as is noted by the two arrows, one going toward the product and the other going towards the reactants. So what happens is when you initially mix nitrogen and hydrogen gas molecules, they react to form NH3. But it gets to the point where the rate is in dynamic equilibrium. So what I mean by dynamic equilibrium is the rates of the forward and reverse reactions are equal. So those nitrogen and hydrogen molecules, those reactants, are combining to form ammonia at the same rate that ammonia is dissociating, meaning breaking apart, and forming back into the reactants, the nitrogen and hydrogen gas. So the rate of depletion of reactants is equal to the rate of depletion of ammonia. So if we want to shift this equilibrium, either way, if we want to shift it towards products or we want to shift it towards reactants, something needs to be done to the reaction conditions. So disturbing a reaction at equilibrium, we have to apply Le Chatelier's principle. So what Le Chatelier's principle says is that when a chemical at equilibrium, so it's only reactions, equilibrium reactions with the arrow going towards the product but also back towards the reactant. If that equilibrium is disturbed at all, the system is going to shift in a direction to minimize the disturbance. So some stressors or disturbances that we're going to apply are concentration. So when I'm talking about concentration, I'm talking about either adding or removing a reactant or product. We're also going to look at a change in pressure, as well as a change in temperature. When we look at changes in pressure, that's only going to affect gas molecules, not aqueous solutions, solids, or liquids, just the gases. For change in temperature, we're just looking at the degrees Celsius, the heat, all of that information. So for concentration, the general rules are if you increase the reactants, you're going to shift to make more product. Okay. Why is this? Well, if I'm adding more reactants, I disturb that equilibrium. I gave more of something, more reactant. If I give more reactant, what's going to happen is that reaction is going to try to get rid of that excess that I added. So in order to get rid of excess, it's going to move towards the products, because if it moves to form more products, it's going to use up that excess reactant that I put in the flask. Likewise, if I decrease product, so now I'm on the product side, so I'm removing product as it's formed. If I remove product as it's formed, I'm taking away something from the product side. So what's going to happen is that equilibrium is going to shift once again towards products because it's trying to replace what was taken. With pressure, only affects gases. So if the pressure has changed at all, just make sure you're only looking at either the reactants or products that have one of those G symbols by them. And we'll go through an example so you can understand a little bit better what I'm trying to say here. So for pressure, we're looking at total moles of the gas considered. I know, moles is in this situation again, but for most of the examples, you will have gas on one side of the equation, but not on the other. So it's going to be very clear as to what's happening. Temperature, if you add heat to an endothermic reaction, that's where heat is on the reactant side of the equation, it's going to move towards product. If you had heat in an exothermic reaction, so that's where the heat is on the product side of the equation, it's going to move towards reactants, giving you less product. Okay, so these are all good in theory, but it's not really going to make sense until we apply it to a chemical reaction, to an equilibrium reaction, and see what happens if we change any of these. So let's look at this example. And I also have this example on the video, but I want to talk through it right now. So in the following equilibrium reaction, how would the following stressors affect the equilibrium? Okay, so notice we have heat. So this is that Q value, calories. It is on the reactant side of the equation. So since it's on the reactant side, that means this is endothermic. So we also have iron 3 oxide, a solid, decomposing into iron solid and oxygen gas. So all of these are going to be important pieces of information to help us. It is equilibrium because we have an arrow going in both directions. So let's ruin that equilibrium. Let's add a stressor. So the first stressor we're going to look at is increasing the concentration of the solid iron. Right, so what that means is that this solid iron, so I'm going to find where that is, and it's on the product side, it's increasing, so it's going up. So if that iron goes up, I just ruined the equilibrium. It's not at equilibrium anymore because I added more iron. Well, what it's going to do is it's going to try to go back to equilibrium. And how it does that is it wants to get rid of what I just added. And in order to get rid of it, it's going to shift towards reactants to the left to get rid of the excess that I just added. Okay, well, let's look at the next one. Increasing pressure. So with pressure, we're going to look at reactants and products that are gases. So the only gas in this entire reaction is oxygen. So by increasing the pressure, what I'm doing is increasing the concentration of that gas, because we looked at this in chapter 5. Increasing pressure makes the gas more soluble, meaning higher concentration. So I increased the pressure, which means concentration of oxygen now went up. Okay, so it's not at equilibrium anymore. To get back to equilibrium, it's going to try to get rid of that excess oxygen. And in order to get rid of it, it's going to have to shift the equilibrium in the other direction towards the reactants. Well, let's see how temperature is going to affect. So if I raise the temperature, what that means is I need to find where the heat is in this equation. And the heat, we said, was on the reactant side. It's endothermic. So I'm increasing the heat in this case. So that's going up. So if I increase the heat, that means the concentration of heat is going up. So disturbing the equilibrium, it wants to get back to normal. It's going to try to get rid of that heat that was added. So in order to get rid of it, it's going to have to shift in the opposite direction, this time towards products. Let's look at one last type. So removing iron. So I'm going to go now over to the product side where iron is. And instead of increasing it, now I'm decreasing it. So let's see what happens there. So I'm going to write a down arrow because I'm getting rid of it. So it's a solid iron, so I can take it out of solution as it's formed. So decreasing or removing that iron, well, I just took something from the reaction. I've disturbed its equilibrium. So what it's going to do is it's going to try to put things back to how it was. So since I took something, it's going to move towards what I took to make more of it. So since iron's on the product side, it's going to move toward products to replace that iron that I took. So here are the answers to all of those disturbances written out. I've also done this example in the video. If you would like to take a look at that, try to kind of solidify this idea.